Welcome, and thank you all very much for coming to the first public lecture this series. As you already heard, my name's Tracy Slatcher. I'm from MIT over in Boston. I've been a general member of the Aspen Center for Physics here for 3 years. So I started in 2020, which in retrospect was not the best of timing. Consequently, this is actually my first time back at Aspen as a general member. I'm really happy to be here. I've been here for about a week and a half this time, participating in the current workshop on new opportunities in high energy physics, for which Masha is actually an organizer. It's been a really wonderful opportunity for many exciting physics discussions, both here at the center and up on the Lost Man Loop on Sunday, where we spent quite a bit of time sitting around attempting to dry out after floundering through several miles of snow. So it's still pretty wintry up there, but we had a good physics discussion as a consequence. One of the most exciting physics discoveries of my career actually came from a conversation here at Aspen. So I'm looking forward to seeing what comes out of this year's discussions. So I want to welcome you all to this pre-physics talk in honor of Heinz Pagels. Professor Pagels received his PhD in physics from Stanford and then went on to a professorship at Rockefeller University. His area of specialization was elementary particle physics, which is also my area and Masha's area. But he was also very dedicated to sharing his science with the public and to promoting public enthusiasm in science. He wrote a number of popular science books. He loved visiting Aspen in summer and visited here very regularly. So this lecture series is in his memory. And tonight we're very fortunate to have as our speaker, Masha Baryakhtar. Masha was born in Kharkiv in Ukraine and then moved to the US in middle school. She did her undergraduate degree at Harvard and then her PhD at Stanford, just like Dr. Pagels, and receiving her PhD in theoretical particle physics. She then went on to postdoctoral research at the Perimeter Institute in Canada and at New York University before taking up her current position as a professor at the University of Washington. Her work focuses on ideas beyond the standard model of particle physics and figuring out new directions to test them. In particular, she's done a lot of really influential and interesting work on the interplay between black holes on one hand and dark matter on the other hand. Two of the most exciting areas in physics, in my opinion. It's sort of two great flavors that go great together. So please welcome Professor Baryakhtar, who's going to tell us about that this evening.
Thank you, Tracy, for the introduction. Thank you, everyone, for being here. It's a great pleasure to give the public talk at the Aspen Center. I've been coming here fairly regularly over the last few years. It's a really wonderful place for discussion and creativity. Today, I'll be telling you about some ongoing work that's in beyond the standard model physics. Connect some ideas from particle theory and astrophysical observations of black holes, try to make new discoveries. As I said, I've been coming to Aspen recently, as she was mentioning, regular weekend activities to go on hikes. But this is from 2 years ago. You can see it was a bit smoky at the time. And this was from another workshop on particle theory. And as particle theorists, we tried to understand fundamental building blocks of what we're all made up of. So in the hairs on my colleague's head, you can zoom in and see the detail where it's made up of atoms. You're all familiar. Atoms are contain electrons, protons, and neutrons. If you zoom in even further, for example, on a neutron, neutrons contain further subatomic particles known as quarks and gluons, pictured here as balls and connecting springs that hold these particles tightly together as a strong force to make up neutrons and protons that are inside all of us. And this has been understood for many years, and in particular, since 10 years ago, we've finished completing the standard model, as it's known, of particle physics. So this diagram contains all of the particles and forces that we know that make up all of us here today. So that includes the electrons, the quarks, the gluons, photons, which carry electromagnetic energy that we are made up of and interact with in a day-to-day life. But it also contains more exotic particles, some of which were not expected. For example, famously, the muon, which is a clear copy of the electron, was known as the "who ordered that" particle because no one was expecting its discovery. Other particles, for example, the neutrinos, came about, which are shown here, came about from theoretical predictions. So we understood underlying laws of nature well enough to realize that something was missing and needed to be added. And that was the theoretical hypothesis of the neutrino in the 1930s, I believe, which eventually led to its discovery. And this picture looks very nice and complete. And indeed, the standard model of particle physics, one of the most precise theories that we have. It describes the world with a great amount of detail. However, we believe there are few particles beyond the standard model that exist. And there's different motivations for believing that there's more out there than what we see around us. One is open questions in the larger scales in our universe. Makes up of galaxies, clusters of galaxies, and the expansion of the cosmos. And all of these particles that I've described in the standard model make up only a very small amount of the total energy density of our universe. Things like dark matter, which we believe could be a new particle or a new set of particles, makes up a larger fraction of the total energy density of our universe. I won't spend too much time on the physics of dark matter specifically today, but if you're interested in that, I encourage you to come back in 2 weeks, where another participant of this workshop, Tanya and Lynn, will be discussing the physics of dark matter and the history of a dark matter particle. Today, I will want to focus on a different open question, which is on the smallest scales. It has to do with similar considerations that led us to the proposal of the neutrino. That there are outstanding questions in the makeup of these fundamental particles that are not understood yet and might lead to the theory of a new particle. So today's talk will be in 3 parts. First, I will tell you the motivation for our belief that there might be new theoretical particles out there. Then I'll talk about black holes, completely switching topics. And in the end, I'll connect the two by describing how astrophysical black holes could actually be used as laboratories for these new particles. So I will try to stop for questions in between these 3 sections, as well as at the end. So feel free to think of questions about the talk. So I've been talking about particles and puzzles and symmetries. What do I mean? So here is me giving a very short version of this talk at a conference for undergraduate women in science that we had back at the University of Washington this year. And if I play this clip, especially if I had the sound on, you'd probably be able to tell that I'm playing the clip we normally would go forward in time. But it's actually a fundamental question about our underlying universe, whether things look the same going forward in time or backward in time. If you go back and watch this video and play it backwards, you'll be able to tell that something's wrong, right? I'm talking funny, I'm moving backwards. You can tell that it's different, and that's a kind of breaking of time reversal symmetry on large scales. But the smallest scales, if you zoom in, for example, if you watch motion of my hands or the motion of subatomic particles inside my hand, you might not be able to tell which way time is going, if I'm playing the movie forwards or backwards. And that's an underlying property of some of the fundamental interactions that we have in our world. For example, we can ask a question: do laws of physics look the same as applied to electrons when we play the movie forward or backward in time? Let's look at this electron cloud that moves across the screen. And then moves back. Did I play 2 movies going forward in time? One with electron moving from left to right, and from right to left? Or was I moving, did I play the same movie forward and backward? If you do very careful measurements of electrons, you'll be able to see that electrons look exactly the same moving forward and backward in time. If you just had electrons and photons in our world, you would not be able to tell the difference if the underlying motion of these particles was going forward or backward. What about other particles, like constituents of the nuclei? Let's look at the neutron. So when we get to the neutron, that's when we get to modeling particles. If we play the same movie of the neutron going forward and backward in time, my excellent keynote skills, it looks exactly the same. And that's actually what we find when we do laboratory measurements of the properties of the neutron. We find that the neutron looks exactly the same going forwards and backwards in time. There exactly is a precise word, by which I mean it looks exactly the same to less than 1 part in 10 billion. That's our current experimental precision. And if you look at that level, you can't tell the difference of whether the movie's going forwards or backwards. Okay, so what's the big deal? Electrons do this, maybe neutrons also do this, right? Our underlying laws of nature are symmetric going forward and backward in time. That's indeed what people believed up until the 1950s. But then it was discovered that some of the fundamental interactions, including the weak force, which the quarks inside the neutron interact with, in addition to other particles, violate the symmetry very badly. We have experimental evidence of that. So quarks, and also we think gluons, don't necessarily respect time reversal symmetry. They don't look the same going forward and backward in time. They have terms in their underlying theory that violate this time reversal symmetry. When we look at the neutrons, which are made up of the quarks and the gluons, it looks like they're exactly time reversal invariant. So how do the quarks and the gluons know to coordinate, make the neutron overall time reversal invariant? That's the weird puzzle that has been around since the late 1970s, when these folks here, Roberta Pecci and Helen Quinn, proposed a solution that was then followed up with by Frank Wilczek and Weinberg, propose a solution which is called the axion. The axion is the new particle that I'm telling you about today, theoretical particle that was proposed to solve the problem of symmetries. So why is the neutron still time reversal invariant, even though it's made up of these two terms, individually are not? So this is being a bit more technical, so bear with me for a minute. Here I'm showing a plot of the energy cost, the function of the amount of time reversal violation. So there's two terms, the quarks and the gluons inside the neutron. If they're in perfect coordination, then you're sitting at no time reversal violation, which is what we observe. And that costs no energy. It turns out that if you deviate from this point, the overall energy of the system becomes larger. And the typical configuration actually has much more energy than this minimum. So this points to a solution. We want some way we can minimize the energy of the system, and then that would point to this nice time reversal metric point that we observe in experiment. So to make an analogy, this is a photo from Mount Rainier, which is a volcano nearby where I live, outside of Seattle. Here you also have many beautiful mountains. If you say, for example, the elevation of Aspen at 8,000 something feet, or the elevation of Mount Rainier, the fixed quantity, just like the amount of time reversal violation in the neutron in the standard model. So, and that tells you some amount of energy, gravitation, in this case, the gravitational potential energy that we all have because we're up here at high altitude. Of course, if we could go down to the center of the Earth, we'd have much less energy. But we can't really do that because there's the floor here. However, if we have a dynamical mechanism to reduce our energy, like the water flowing down the hill in this photograph, then you can dynamically change our energy to try to minimize it. The axion does something similar, even though in the standard model without the axion, the energy of this configuration is fixed. It's some initial condition that typically has a lot of energy, just like the elevation of Aspen. Axion is like the water flowing that can flow down the hill into the ocean and minimize the energy. So this particle was proposed in the late 70s. We've been looking for it ever since. We discovered it would likely be the lightest particle ever discovered. We don't know exactly the masses of the neutrino, so I can't tell you for sure. Unfortunately, we don't know a lot about its properties. We know a lot about its interactions, it couples to quarks, to gluons, but its mass can be in a really wide range. Mass can be on the heavier side, although still light. This would be in the range of about 1 million times lighter than the electron, to much lighter, about 1 million times lighter than the electron. The theory does not have a sharp prediction for the value of this mass. Such light particles, it makes sense to think of them as waves because their wavelength is really becoming macroscopic. Quantum mechanics tells us that for a particle, the more massive it is, the shorter its wavelength, and the less massive it is, the longer its wavelength. It's similar to how blue light, which has a short wavelength, has more energy than red light, which has a long wavelength. So what's the wavelength of this axion particle? Theories tell us that it can be between about 1 millimeter or thousands of kilometers. That's a really big space to try to look for a new particle, which is why we need many different approaches to look for it. It could be almost as short as the wavelength of visible light. The wavelength of an axion could be the size of a teacup, could be the size of a mountain. Each of these scales require different experimental search strategy to try to look for it, just like you need different types of telescopes to look at visible light or to detect radio waves or detect X-rays. So this concludes my motivation for the axion particle, and I just want to stop for a minute to take any questions that you might have about this section. Yes.
If you don't know that the particle actually exists, how long would people look for this before giving up?
That's a great question. I'm supposed to repeat the question. If we don't know how long if we don't know whether the particle exists or not, how long do we look before giving up? That depends on who you ask. There are some concrete goals looking for this particle. So we know there's a range of masses that's interesting. We also know how it interacts with other particles, for example, how it interacts with light. And so if we're able to reach that target of how often you would expect it to show up in interactions with light, then you can exclude some parts of that parameter space. So I would say if we cover all of that parameter space, so you look at all of the masses where it might be with the expected type of interactions with a standard model, then you would exclude this type of particle. And at that point, you might give up and say this is not the right distribution. That said, there are caveats to all of these. For example, some of the searches depend on some assumptions. For example, if this particle is the dark matter of our universe. So there are different goalposts. And if you have a really great idea of how to look for it, then I would say that it'd be exciting to continue looking for it. Yes.
You have an energy movement here. Is there any way that you can capture the energy as a new source of energy?
Is there any way that we can capture this energy as a new source of energy? It's difficult because the axion is very, very weakly interacting. In principle, if the axion is the dark matter, there is a large amount of energy captured inside the axion all around us. But the rate that you can convert that energy to something that we can use is very small. For example, at the heavy end of this range, if you do the best that you can converting the axion to photons, you'd see about be able to pour a light bulb, which is best case scenario. Everything else is much, much worse. So in principle, there could be, if things work out just right, there might be some clever ideas, but mostly types of particles are kind of invisible to us, and so it's hard to make use of them directly. Other questions? Yes.
How do you simulate the reversal of time in a lab?
Oh, great question. How do you simulate the reversal of time in a lab? Yes, I kind of skipped over that because it's really technical, but basically what we do is, or what experimental colleagues do, they don't simulate the reversal of time. They look for a property of the neutron that violates time reversal symmetry, and that property is called the electric dipole moment. So the electric dipole moment is the displacement, the asymmetric displacement of charge inside of the neutron, which is predicted to be exactly 0 if time reversal symmetry is there. And so if we detect the presence of that electric dipole moment in the lab, which is done by observing the interactions of neutrons with electric and magnetic fields, then we can map that onto the amount of time reversal. Yes.
Is there any detectable interaction between the axion and other particles?
Is there any detectable interaction between the axion and other particles? Yes. So as I was alluding to in the answer to the first question, axion is predicted to interact with quarks and gluons, as well as with photons, with light. The degree of that interaction is very small. So compared to, say, electrons, which interact a lot with photons, axions interact much, much more rarely. So there is a specific prediction, but it's sometimes very difficult to reach that level of interaction in our experiments. So let me move on to the next part of my talk, and I'll also take questions at the end. More questions on this part. So changing gears, I want to talk about black holes. So going from the world of subatomic particles to the world of extreme astrophysical objects. There are black holes. I think there's also some other lectures on this topic later on in the series, so I'm sure you'll learn lots of different aspects if you keep coming back. Let's start with something more simple that we all know, the Earth. So we're standing here, and the Earth has some amount of gravity, quite a lot, which is why it's hard to hike up those mountains. If we try to escape, we need to jump up with a velocity that's called the escape velocity, overcome the potential energy, the Earth's gravity. That's about 11 kilometers per second. So that's me jumping. That's very fast. It's about 25,000 miles an hour. So that's going to be pretty difficult, especially at this altitude, to get that much energy. And that's due to that's a combination of the mass and size of the Earth. We have more mass, like in the sun. If you're standing on the surface of the sun, which I don't recommend doing, very dangerous, you'd have to jump up much faster at about 600 kilometers per second or 1 million miles an hour to escape the gravitational pull of the sun. That's because the sun is much more massive than the Earth. You take that mass of the sun and concentrate it, for example, at the end of life of many stars, they explode and leave behind a very dense remnant of the neutron star, which has about the mass of the sun, but in a much, much smaller radius, and a much smaller size. So it's very compact. So you're feeling all that gravity much closer to you. So the escape velocity from a neutron star, it has the same mass as the sun, becomes much larger because you're feeling gravity from a much more shorter distance from the center of the neutron star. And this is about 20% of the speed of light. You're standing on the surface of the neutron star, aside from the fact that you'd probably get crushed. You would need really a lot of energy to escape. But light can still escape the neutron star. Now, if you have a black hole, the defining property of the black hole is that its escape velocity is equal to the speed of light at the surface. So that means that not even light can jump up fast enough from the surface of the black hole to escape it. And of course, the speed of light in the special theory of relativity, and as far as we can tell in our world, is the ultimate limiting speed, so nothing can escape. Something enters the black hole, it's going to be absorbed, it's not going to leave. So black holes are the ultimate absorbers. Another interesting property, and this is I should say this is an image, a simulation of the black hole that's in the middle of our galaxy, in the middle of the Milky Way, called Sagittarius A star, which we have been observing with telescopes to try to image the gas around the black hole. The black hole itself, of course, you can't see, but you can see the motion, things around the black hole, and from that inference properties. The other interesting property of black holes is that they can rotate close to the speed of light. Normally, if you or I rotate, it can be hard to spin up really fast. If you start spinning up any object really fast, eventually it'll start flinging off pieces of itself because it's not bound tightly enough. The black hole, you can keep spinning until it's basically spinning at the speed of light. Black holes can absorb very well and can spin very fast. So they're characterized, I'm hinting here, they're characterized by two numbers. They're characterized by the mass of the black hole and by the spin. So how heavy it is, that's how big it is, where is its horizon, which is the point from which no light can escape, and how fast it's rotating. They're very dense. So the mass of a sun can fit inside a 3-kilometer radius. And in addition to the very massive black hole that's at the center of our Milky Way, we believe there are as many as 100 million solar mass black holes with mass similar to that of our sun, flying around our galaxy. These are the remnants of dead stars that are invisible, but exist all around the Milky Way. So a black hole is an impressive object, so it can contain mass of the entire sun and basically fit in downtown Aspen. Very dense, and you can have quite interesting properties. We're living in the era of black hole science, so you might have heard that 2015, we for the first time detected gravitational waves from the merger of two black holes. So there's a video of that shown here of two black holes, a bit hard to see, they're coming together, and the green waves are the emission of gravitational waves, which are ripples in space and time that get stronger and stronger as black holes get closer together. And eventually, black holes will merge, producing a burst of gravitational wave radiation that then travels out to us on Earth, and we detect with the LIGO and Virgo gravitational wave detectors. The first discovery was in 2015. By now we're doing gravitational wave science. It's incredible how from the first time we've observed it to today, we've already seen around 100 black hole mergers. So here's a catalog of all of them. There are different masses. You have two smaller black holes merge and create a bigger black hole. This is allowing us to study properties of stellar evolution. We're trying to understand populations of these objects. With future detectors, we might be able to see all the way out to the edges of the universe, all of the black holes that have ever merged throughout time. So it's pretty amazing how fast this field is progressing, and it's going to allow us to do more than black hole science, to also do particle physics. So before I move on, are there any questions on black holes? Sure, there's lots of questions, but limited to a few. Yes.
So how can black holes absorb so much light and still remain completely dark?
How can black holes absorb so much light and remain completely dark? So they absorb the light, but once the light is inside of the black hole, it can never come back out because it would have to travel faster than the speed limit, the speed of light, to get back out. So you only see light from that light bulb because there is light, photons, particles of light coming from that light bulb to your eye. If there's no particles of light coming from the black hole to your eye, you're never going to see it. So if they're all trapped inside of the event horizon, it's never going to come out, hit your eye or your telescope. Questions?
So what happens to all the light that's inside of a black hole?
What happens to all the light that's inside of the black hole? That's a great question. So we don't know exactly. Eventually, all of the energy that goes inside. First of all, if you put more energy in the black hole, it'll get bigger. The black holes can grow. That happens a lot if you have, for example, matter around it or another star that falls in. Black holes can grow and get more massive. They can start spinning faster, but we don't actually know exactly what goes on the very centers of black holes. The place called the singularity, that's where our theory breaks down, because that's a place where both where general relativity no longer applies, and you have to combine it with laws of quantum mechanics at very small scales. So these are kind of unanswered questions of what happens in the very centers of black holes, and that drives a lot of research in theoretical physics in the field of quantum gravity. Yes.
Are black holes fundamental to the origins of the universe in terms of the Big Bang? I realize this is probably a subject all by itself.
Are black holes fundamental to the origins of the universe? In the strict sense, I would say no. So the black holes that we observe around us in our universe are all the product of dead stars and mergers of dead stars. So this happened relatively late in the history of our universe. So first we had to form galaxies, then gas in the galaxies had to clump and form stars, and those stars had to live for millions or billions of years, collapse and form black holes. For most of the universe's history, there actually weren't that many black holes. That said, some of these questions, like I was referring to about quantum gravity and black holes, might be connected to the origins of our universe. Theoretical studies of properties of black holes might also shed light on the earliest times. But experimentally, there's no direct connection. Yes.
The excitement about Hawkins radiation, the escape, what is that all about? Why the excitement?
Why the excitement about Hawking radiation? It's again connected to these themes. So Hawking radiation has to do with some properties of black holes that are not there in just standard general theory of relativity, but that come up once you introduce particles and quantum mechanics to black holes. And so there, I'm mentioning that black holes can always grow when they accrete mass and other matter falls in. Typically, they can't shrink because nothing can escape. If you have Hawking radiation, that's actually this faint glow of particles around black holes that can slowly dissipate the mass of a black hole, and eventually it'll shrink to zero. So it's very counterintuitive in the picture of general relativity. But now we understand it really well. It's never been observed because this emission is very, very faint, especially for astrophysical black holes. It connects to these questions of how you connect black holes and mechanics together. Right. I'll save more questions on black holes for the end of the talk, and I'll move on to the last part, which is thinking about how to use these wonderful observations that we have black holes that we've acquired over the last few years to say something about the nature of new particles. To do that, first I have to teach you a new concept, which is called superradiance. And superradiance is all about how to use energy loss for energy gain. This might be a bit counterintuitive, but let's first start with a simple example of friction. So for example, if you're walking down, running at the airport, you're late for your flight, and you're running down one of those moving walkways, and you slip, and you start moving forward, and the friction of the moving walkway will slow you down. You're losing energy because of friction. However, if you start slipping, if you jump and start slipping kind of slowly compared to the motion of the moving walkway, and the walkway ends, you'll actually come out with a bit more energy than what you started. You feel a little shove from that moving walkway, because the walkway transferred some of its energy to you through the force of friction between your feet and the walkway. If you have a relative velocity, if your motion is slow compared to the motion of a moving object, there's some friction between the two, you can actually extract energy from that object. That can also happen when you have rotational motion. If you have, instead of flat walkway, you have a cylinder. The cylinder has a bit of a rough edge around it. The cylinder is at rest, and you throw a ball at it, the ball will come to a stop because of, or slow down, because of the friction between the ball and the rough cylinder covered in sandpaper. However, the cylinder starts rotating. It's rotating fast enough. The relative motion between the surface of the cylinder and the ball will be such that the ball will feel a kick going forward. It will extract some energy of the cylinder, and in the process, it will slow down the rotation of the cylinder. So if you have an object that's rotating quickly, it can cause things that come in contact with it to speed up. This only happens if the rotation is fast enough compared to the motion of the other, whatever is impinging on the cylinder. Here I've been using examples of people and balls, kind of particle effects where you get thrown forward. This also happens with waves. It's actually experiments that have been done in the laboratory where you have water waves around rotating drain in the center here. So these are movies of water waves that are inside of a rotating cavern with a drain that's simulating the energy loss process. So water drains through the hole in the middle. Because of the rotation, the waves on top of the water actually start to amplify rather than decrease as water flows through the center of the hole. So if you have a relative rotation between your cylinder in which you have the water and the velocities of the waves, you can actually get some amplification of the waves in the system, which is a kind of a strange concept. Usually when you have losses, you expect things to decrease. But if you have this quickly rotating object, you can extract its energy, continue amplifying the waves in the system. So these are actual experiments that have been done to demonstrate this process in the lab. More exciting for us, this process can happen around black holes. So if you remember what I said last part of my talk, black holes have a lot of energy and can rotate really fast, and they absorb everything. So if this extraction of energy comes from rotating really fast and absorption, then black holes are the perfect sources of energy. And in fact, here I'm going to show a simulation that's been done in general relativity of waves coming to a black hole. The waves will be starting to come in colored in blue, and then they'll get amplified. The outgoing waves are colored in red, just to show you the difference between incoming and outgoing. Colors are not the actual color of the wave. You can see the outgoing radiation is much, much stronger than the incoming radiation. Let me play that again. You have these waves that are coming in, they're scattering from the black hole, and they're coming back out. Because of the black hole is rotating very quickly, as is assumed in the simulation, and because it's absorbing waves that are coming at it, if you look from far away, the black hole is actually slowing down because of this absorption effect and increasing the amplitude of the waves, like the water around the drain. This process is a completely classical process that happens in general relativity. We expect it to occur, and it's included in, for example, simulations when we look at mergers of black holes. But the interesting thing for us is that if these waves have a mass, like the axion does, then the waves can become trapped near the black hole. So here, instead of showing what happens with black holes generating, amplifying these waves that come in and rescatter, as I showed in this simulation, I'll show what happens when black hole amplified axion waves. The black hole starts vastly rotating, and it grows this cloud of axions around it. Here I'm showing the colors represent how much energy is in axion. So brighter is more energy, darker is less energy. And here, because the axions have a mass, it can become gravitationally bound to the black hole and stay as this cloud of particles, continuing to extract energy. This process to me is completely mind-blowing, but you can calculate it. It makes a lot of sense once you sit down and think through these analogies. And if the axions exist, then we predict that black holes will spin down and source these clouds of axions. This is what I just said. If particles have a mass, they will stay trapped near the black hole and continue spinning it down through this process of gradients, energy extraction through energy loss. The cloud of axions will grow, and the black hole will spin more and more slowly. Of course, once the black hole is spinning slowly enough, its energy extraction shuts off because you need that fast rotation for the process to happen. At some point, it will stop. Typically, what happens is that there's a lot of energy sitting around the black hole, and fast black holes will become slow. So by measuring how fast black holes in our universe are rotating, we can exclude or detect the presence of these particles. And the other interesting thing is that once you have these giant clouds of particles around the black hole, they can contain as much as 10% of the mass of the black hole. These particles will also themselves emit gravitational waves. Just like the black holes that I showed you merging earlier, the gravitational waves, these axions are all spinning around the black hole, and that rotation, that energy will create ripples in space-time. Here is okay. Well, you can imagine that these waves are propagating out from the black hole. So there's two things that we can measure. We can measure how fast black holes are rotating. If they're rotating quickly, that means there aren't any axions to spin them down. We can exclude the presence of axions. We can also look for gravitational wave emissions. For example, let's take two black holes. So here on the top panel, I'm showing the history of a black hole. And on the bottom, I'm showing the amplitude of gravitational waves. So how much is space shrinking and stretching. At the beginning, you have these good-sized gravitational waves like the ones we detected. I mean, they're still really, really tiny, but we know how to detect them now. As the black holes are coming closer and closer together, these gravitational waves get louder and louder. Eventually, when the gravitational waves merge, there's this big burst, and then everything is quiet. But if there are axions that can spin down the black hole, what happens then is the black hole grows this cloud of particles around it, and this cloud of particles will start emitting gravitational waves. So if you wait some time, you'll see these small but very long-lasting gravitational waves that are coming after these hundreds of mergers that we've observed. So if our instruments are good enough to detect these very tiny gravitational waves, it could be signals of axions around black holes. That's work that's happening right now. People in LIGO and Virgo are looking for these signals. And especially with upgrades to the detectors, you might be able to see these tiny signals at the end of black holes, the end of a black hole merger, could be evidence of a new particle. Just to give you a sense of where that would be, that would not tell us whether axions exist generally, as to your earlier question. This would only probe part of the parameter space. So in this parameter space from wavelengths of thousands of kilometers to about a millimeter or micrometer, black holes can tell us whether axions exist in a range of parameter space of about a factor of 100 or maybe 1,000 if we're very precise in our measurements. So these can inform some of these theories of axions and potentially be used to discover new particles with gravitational waves in black holes. So I'll stop there. Today we talked about searching for new particles in the sky using black holes. We talked about how we are starting to answer these questions about underlying symmetries of particles on the smallest scales, properties of particles that we're all very familiar with, neutrons that are inside all of us, are actually quite puzzling, given our understanding of the universe. And trying to solve these puzzles leads us to predict a new particle, which is called the axion. And the axion is a very elusive particle. It doesn't like to interact much with any of the particles that you and I are made of, so it's hard to detect. But perhaps these magical objects, black holes that we see all around us today, the power of gravitational waves, can be used to help detect it. So thank you, and I'm happy to take more questions.
So what part of the black hole is actually rotating, and then how does that energy transfer happen?
Good question. So what part of the black hole is actually rotating, and how does that energy transfer happen? The black holes are a bit weird because they're not objects that you can think of like you and me or the sun, where they're made up of stuff that's rotating. Black holes you can think of as extreme curvature of space and time. So what's happening is that the actual space and time around the black hole is rotating. And so you can define rotation speed of the horizon relative to when an observer is standing very far away. When we talk about what's rotating, it's when you come close to the black hole, anything that comes very close to the black hole will be rotating because space and time itself is rotating. So when you have the superradiance process, what happens is that rotation is slowing down and that energy is getting transferred to these particles in the cloud. And this was first understood by Soviet physicist Zeldovich, made the analogy with other rotating objects. People didn't, he was a very intuitive physicist, and he realized that other objects could do this, like I described with the water in the drain. He said, well, if other objects can do this, black holes should also be able to do this. For a while, people didn't really believe him because they couldn't understand what exactly was rotating and slowing down. But when you sat down and did the calculations and general relativity, you could see that this process is actually happening as he mentioned.
So is the axion the leading candidate now for the composition of dark matter, in your opinion?
Is the axion the leading candidate for the composition of dark matter? In my opinion, yes. But you could probably as many opinions as there are people at this workshop, at least. It's a great dark matter candidate because it's automatically produced in the early universe, and also it's stable, weakly interacting, and it's motivated by these other considerations that we have for the solution to this universal problem. Of course, that doesn't mean it's the dark matter. There are many other very interesting candidates. You'll probably hear some of the other ones this time as well.
Can we have any idea as to the time span for the merger of two black holes?
Do we have any idea for the time span of the merger of two black holes? Yes, we are starting to understand it pretty well. It depends on what you mean exactly on the time span. So we know exactly how the merger happens once the gravitational waves are at frequencies that our detectors can see. And so the observed merger is usually just a few seconds. But we think black holes start out their life as remnants of dead stars that were originally in a binary, and there'll be some distance away. And over very, very long times, they'll slowly orbit together, eventually get close enough that they're orbiting fast enough so that we can see those signals. How long that takes depends a bit on basically just the initial properties of stars and how far away they are. It can take anywhere from 10 million to 10 billion years. We'll only see the black holes that merge fast enough that they merged in the lifetime of the universe.
Cool. Is there a specific direction that you measure that they spin in? And number two, the black hole itself is traveling at the speed of light through space. Is that not correct?
So there's a two-part question. Let me answer the second part first. So the black hole itself traveling at the speed of light in space. The answer to that is no. Black holes are traveling in our galaxy at similar speeds to other things in our galaxy, which is about 1 part in 1,000 of the speed of light, roughly 200 kilometers per second. Some of them might be going a bit faster because when the star exploded, it could have given it a kick. It goes a bit faster. Black holes are, if you're far enough away from them, they look like any other object. And it will take infinite energy because they have mass to accelerate them to the speed of light. The other question was, what's the direction of the spin of the black hole? And we do measure that, for example, from the properties of the gravitational waveforms. If you measure this very carefully, you could see something about the spins of the black holes in the data analysis. Direction in which it's pointing is random. It depends on, what stuff fell into the black hole. As when the star exploded, the star initially was rotating like our sun is rotating. So some of that rotation will remain in the black hole as well. So it kind of depends on what we call initial conditions. So how the black hole started out its life. And it could point in any direction, but it will be stable over the course of its life.
Why is it flatlined there? After the merger of the black hole?
Yes, so why is the signal flatlined? So in here, so this is just the signal. I'm not showing real data, which is much more noisy, just to be clear. So the signal itself is there's no more gravitational wave emission because the black hole itself is perfectly round, doesn't emit any gravitational wave radiation. The gravitational wave radiation, you need some asymmetry in the object that's rotating. And
The wave unless you have two.
you don't get a wave unless you have something clumpy. So it can be two things. It can be something that's asymmetric. If I rotate, I'll generate some gravitational waves. Be very small. Black hole does not. Yes, that's one of the interesting properties of black holes is that they're perfectly symmetric in this direction, and so they don't emit gravitational waves on their own.
Yes.
Yeah. Yes.
Any understanding of a relationship between the axion and so-called dark energy?
Is there any understanding between the relationship between the axion and dark energy? There are some models of dark energy which say that it could be very, very, very light axion. If your axion is very, 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 very light, much lighter than the range I showed here, so it wouldn't be axion that couples to quarks and gluons and solves this neutron problem. It's some other particle that's similar to that. It could behave like dark energy. It wouldn't really, in my mind, solve the problem of dark energy because we'd still have to explain why there's so little of it from all of the other. So if you've read anything about dark energy, if we do the calculation from particle physics, we predict it to be very, very large, but we actually measure it to be very, very small. So it wouldn't explain why very, very small. It would just say, oh, there's some contribution from the axion, from an axion. There could be connections, but or a component of dark energy could be a very light axion, but that would still leave a lot of the questions. Questions? Yes.
What's the time span from the merger that the black holes to when you would be able to detect super radiance?
Great question. What's the time span between the merger and when you'd be able to detect superradiance? It depends a bit on the properties of the axion. So in the interest of time, I didn't go into the parametrics, but if the axion mass is in that range I showed you, it could be between a few hours and a few years, depending on what the wavelength of the axion is. The process is more efficient if the wavelength of the axion is close to the black hole size. Remember, I was telling you that stellar mass black holes have sizes of about kilometers, and these axions can have wavelengths of about kilometers. So that's why we're probing those axions most efficiently, because they grow quickly. The axion wavelengths are very long, and this process is less efficient, and this could take millions of years, and then we wouldn't see it. Yes.
One more question. At the center of the Milky Way, you have a supermassive black hole. And one of the physicists lists all the things that are rotating around it, and yet they don't emit gravitational waves. Explain.
So the question is, there's the black hole at the center of our Milky Way, and there are all the stars that are rotating around it, which is actually, I believe Andrea Ghez was here to give the talk about how she did these measurements that led to the discovery of this black hole. Those stars actually do emit gravitational waves. Anything that orbits emits gravitational waves. Actually, the Earth rotating around the sun emits gravitational waves. But just the amount of gravitational waves that are emitted, the objects are light and moving relatively slowly, like the Earth is pretty light compared to the black holes that are emerging here, are very small. So it's just very, very slow, and we don't detect it. But they are being emitted. They're just too small to detect.
Well, I think we're at 6:30, so we might wrap up there. Let's thank you, Professor Baryakhtar. Thank you all very much for coming and for all the great questions.
Thank you for the great questions.